Hello everyone, I'm Qi from the Chinese University of Hong Kong. This paper is GTuner tuning DNN computations on GPU via graph attention network. This work is done by cooperating with Xingyun Zhang, Yuxuan Zhao, Yang Bai, Beiyu from the Chinese University of Hong Kong, Hao Geng from Shanghai Technology University, and Haisheng Zheng from Smart Mall. Here is the background of this work. TVM is a popular deep learning deployment platform. It's a typical learning-based optimization system for deep learning models. The inputs are DNN models in the format of TensorFlow, PyTorch, and so forth. The input models are firstly analyzed as the high-level data flow graphs, and then do the graph-level optimizations. In this step, the input models are analyzed, optimized, and converted to the intermediate representations. Then the hardware-aware search space for the tensor programs is defined. We can use the machine learning-based models as the program optimizers. The optimal tensor programs learned by the machine learning models are compiled and executed on the target hardware. There are many target hardware platforms such as FPGA, GPU, CPU, and mobile phones. Here are some concepts in the deep learning deployment flow. Computational graph. A deep learning model to be deployed is represented as a computational graph. Subgraph. A deep learning model is split into some subgraphs after the graph optimization. Each subgraph can be implemented as a tensor program, which is computational kernel on GPU. Here are three typical computational subgraphs. Here are some optimization techniques such as operation fusion, constant folding, data layout transformation, and so forth. Sketch. The code templates designed by compilers to implement the computations of a subgraph are termed sketches. Each subgraph has many code templates. In other words, for each computational subgraph, we have many code sketches. Annotation. The combinations of the parameters to be determined in the sketch are termed annotations. In other words, each sketch has many annotations. Here are some examples. The first figure is the code template, or we say code sketch. And there are some parameters to be determined in this sketch, such as boundaries of the loop. The second and the third figures are two annotations. The loop boundaries have determined values. We can synthesize these two annotations to generate the executable files. In our optimization problem, the target is to find the optimal annotations for each subgraph in the deep learning model. There are some previous R's, and the algorithm flow is shown here. The schedule space, which is the design space for the codes in our problem, is built for the deep learning expression. An exploration module is defined to tune the codes. Simulated annealing and genetic algorithm are typical exploration algorithms. The cost model is based on the historical data to predict the performance of the new designs in the design space. AutoTVM builds the basic framework. Chameleon use reinforcement learning and adaptive sampling during optimization. GGA designs the guided genetic algorithm according to the similarities between the history and the new designs. DGPTL use the deep Gaussian process and the transfer learning algorithm. ANSO proposes the sketches and the annotations, and therefore covers more and better designs compared with the previous R's. Our work is based on the ANSO. There are some challenges to be tackled. Firstly, the structural information of the subgraphs is not used, and researchers only rely on the statistical features. It's difficult to use these features to identify task information and distinguish different tasks. Secondly, the complicated relationships between the features are not considered. The traditional cost models such as XGBoost and MLP treat the statistical features equally, despite their physical meanings and relationships. To tackle these problems, we propose a novel method, GTuner. The contributions are extracting statistical and structure features for the annotations and proposing a graph attention network composed of a graph neural network and a multi-head self-attention module. In the graph optimization step, we represent the optimized subgraphs as intermediate representations. We implement a directed acyclic graph analyzer to analyze the IRs to construct the optimized subgraphs. Then we generate and sample codes to initialize the models. We extract structure and statistical features for the codes and do the performance learning via a graph attention network. Then the graph attention network is used as the performance estimator in the genetic-based iterative optimization step. Here are the details of the graph attention network. We define a graph neural network to extract the structure features for the computational subgraphs. The statistical features are concatenated with the structure features and are used as the inputs to the multi-head self-attention module. The inputs to the graph neural network are the information reported by DAC analyzer. The input features include the computational types, inputs, outputs, dimensions, and so forth. The representations of the nodes are updated by aggregating information from their neighbors. An important target is to distinguish the different model structures. Therefore, the concept of the WL test is of vital importance. The WL test can distinguish isomorphic graphs via information propagation and can identify the structure similarities between graphs. In this paper, we choose to use the graph convolutional layer named WLGCM. Here is the aggregation and the combination function, where W1 and W2 denote the learnable weights. The mean pooling layer is used to aggregate features from all of the nodes to achieve the feature embedding for the computational subgraph. Transformers have achieved great success and become the best choice for many natural language processing tasks. Further inspired by the NLP successes, many works unveiled the potential of multi-head attention, which plays a crucial role in transformers for computer vision tasks. Here is the structure of the multi-head attention. And in this module, an important concept is the scaled dot product attention. There are three inputs, Q, K, and V, representing the query, key, and value matrix. Each head is defined as an attention module with inputs Q, WQ, K, WK, and VWV, where the W matrix are the learnable projection weights. Then the multi-head attention is the concatenation of the multiple heads. Each query vector of Q can attend to all of the key vectors of K and compute the attention scores concerning these key vectors. The final outputs of the attention module are the weighted sum of the value vectors of V, with attention scores as the weights. To fit the multi-head attention, we reshape our input vectors into some shorter vectors. Denote the original input vector as X with the length L. Then we reshape it into H shorter vectors denoted as XR. Each short vector has a length of L to H. H is the number of heads. XR is used as Q, K, and V. Therefore, we have self-attention module for our task. The products in the self-attention characterize the similarities between the feature vectors and reflect the implicit relationships among these features in XR, including the scheduling of the subgraphs and memory patterns. Here are the experimental results. We conduct experiments on an NVIDIA GPU with CUDA PyTorch and TVM 0.8 development version. There are about 170,000 annotations in the training dataset collected from Inception v3 and the VGG11. Our GAT model has two WL GCN layers, a mean pooling layer, a concatenation layer, a FC layer, and a four-head self-attention layer, and an MLP module for regression. We do some application studies on the graph network. We tested three layers. The first one is spectral graph convolution. It's a first-order approximation of spectral filters and lens filters to represent the nodes in the Fourier domain. The second one is the masked attention convolution. It introduces the attention-based architecture to compute the hidden representation by using masks during information aggregation. The third one is GraphSage. It generates embedding by sampling and aggregating features from a node's local neighborhood to improve the generalization ability. Compared with our results, using these modules achieves worse results. These modules use approximations and force the models to ignore some information to improve the generalization. Therefore, they degrade the performance significantly. We also do some ablation studies on the model structures, that is, whether using the multi-head attention module. It's shown that compared with the baselines, using a multi-head self-attention module has significant performance improvements. We do some ablation studies on the trials of the genetic-based optimization. Longer optimization trials can help find better results. We test ENSO and our method on ResNet 18. The results show that our method always outperforms the baseline. We also compare the performance of the subgraphs. It shows that our method wins on most of the subgraphs. Finally, we show the performance results compared with more baselines, PyTorch with GIT, TDM, ENSO, MHSA, and our GTuner. The results show that our method outperforms the baselines significantly with up to 13.98% latency reduction. As to the optimization time costs, our method has similar costs compared with ENSO and MHSA, and is lower than AutoTDM. These are all of my presentations, and thank you for your listening.